Okay, in this video we will see the remaining part of optical isomerism. So in the previous video we saw that there are two type of optical isomers, dextro and levo, represented by a small d and a small l. So dextro rotates the plane towards right hand side and levo rotate the plane of the plane polarized light towards left hand side. Now if we have a mixture in which we have 50% D form, 50% D isomer and 50% L isomer. That is, we mix dextro and levo in equal amounts. Say if 5 gram is dextro, then 5 gram is levo. That is, when we mix equal amounts of dextro and levo, then this mixture is called racemic mixture. So racemic mixture is a mixture of equal amounts of dextro and levo, that is equimolar mixture. Equimolar mixture means in which we have equal moles of dextro and levo. So racemic mixture is an equimolar mixture of dextro and levo isomer. That is 50% is dextro and 50% is levo. Say 5 gram, 5 gram, 1 gram, 1 gram. So when equal amounts of dextro and levo are there in a mixture, we call it racemic mixture. And racemic mixture, suppose we have 50% D isomer. So all the D molecules will try to rotate the plane. Suppose this was the original plane. So they will try to rotate the plane towards right hand side. For example, they rotated the plane towards right hand side by 30 degree. Right? So this was the original plane and they rotated the plane towards right hand side by 30 degree. Then what will 50% levo molecules do? They will rotate the plane towards left hand side by 30 degree. That is, again the plane will come in the original direction. So if 30% is rotated towards D and 30 degree is rotated towards right hand side and 30 degree is again rotated towards left hand side, it means the original direction will be restored. That is, in equimolar mixture, half of the molecules will try to rotate the plane towards right hand side and remaining half will rotate it back towards left hand side. So this way the net optical rotation, that is the net rotation, will be 0. Why? Because the rotation caused by dextro is being compensated by levo. दैट इज़ जितना वो राइट हैंड साइड घुमा रहे हैं वो वापस उतना लेफ्ट हैंड साइड घुमा दे रहे हैं. सो इसका मतलब कि देयर विल बी नो नेट ऑप्टिकल रोटेशन. दिस इज़ व्हाई आई सेड नेट ऑप्टिकल रोटेशन विल बी 0 and this is said to be external compensation. This phenomenon in which the rotation caused by 50% D is compensated by 50% L, we call it external compensation. So if we say that why is racemic mixture optically inactive, since it is not rotating the plane finally, so this will be optically inactive. So what is the reason of being optically inactive? Racemic mixture is optically inactive due to external compensation, which means the rotation caused by 50% D is compensated by 50% L. So net rotation will be 0 here. So this is the concept of racemic mixture. Racemic mixture is 50% D plus 50% L and it is optically inactive due to external compensation. Now if you have all D isomers or you have all L isomers and you are converting it into racemic mixture. That is, if D is converted into racemic mixture or L is converted into racemic mixture, then this conversion of D or L into racemic mixture, this phenomenon is called racemization. So what is racemization? Racemization is the conversion of D isomer or L isomer into racemic mixture. If you convert D into racemic mixture or you convert L into racemic mixture, this phenomenon will be called racemization. And the reverse, if racemic mixture is given to you, you already have racemic mixture and you are separating it into D and L. रेसिमिक मिक्सचर में दोनों एक साथ है, अगर आप दोनों को अलग अलग कर लो, दैट इज द सेपरेशन ऑफ D and L from a racemic mixture. If a racemic mixture is given to you in which D and L are mixed together and now you are separating them. So separation of D and L from a racemic mixture is called resolution. So when D and L is given to you and you want to make racemic mixture, the phenomenon will be called racemization. And if racemic mixture is given to you and you are separating into D and L, that is एक container में D isomer, एक में L isomer, the separation is called resolution. So these are a few important terms: racemic mixture, racemization, and resolution. After this, we are going to do the optical isomerism in two important compounds which are there in ISC course. The first is optical isomerism in lactic acid. Lactic acid has the IUPAC name 2-hydroxy propanoic acid. So you can be given the question with the name lactic acid, or you can be given the name with the question with the name 2-hydroxy propanoic acid. So let us first draw its structure. I will first draw the linear structure. Propanoic acid. Prop means a 3-carbon chain. Ane means all the bonds are single. Oic acid means one carbon will be converted into COOH, and 2-hydroxy means on the second carbon you have hydroxy. So you will satisfy the rest of the carbon by required number of hydrogen. Now you can see this is the structure of lactic acid, which is called 2-hydroxy propanoic acid. Now this carbon is chiral. Why? Because this is connected to H, first group, OH, second group, CH3, third group, and COOH, fourth group. That is, this carbon is connected to 4 different groups. One is H, another is OH, third is CH3, and the fourth is COOH. And this carbon, which is connected to 4 different groups, is called asymmetric or chiral carbon and is represented by an asterisk sign. So this carbon is chiral, and there is only one chiral carbon. Therefore, we will not check the second condition, which is to have a plane of symmetry, or it doesn't have a plane of symmetry. So plane of symmetry is seen only when there are 2 chiral carbon. There is only one chiral carbon. Therefore, only one condition is required to show optical isomerism, that chiral carbon should be present, and we have seen it is present. So lactic acid or 2-hydroxy propanoic acid will exhibit optical isomers, will exhibit optical isomerism, and The optical isomers of the lactic acids will be two. One will be dextro and one will be levo. The first isomer is D-lactic acid and the second isomer is L-lactic acid. You can write it complete words also, dextrorotatory and levorotatory, or you can write plus or L is minus. So how do we draw the lactic acid, dextro and levo? Let us understand. Carbon is chiral carbon which is connected to four different groups. One is hydrogen, one is hydroxyl, one is methyl and one is COOH. So what you have to do is to draw dextrorotatory. At the top you will draw CH3, at the bottom you will draw COOH. On the left you will draw H and on the right you will draw OH. This way you have to draw methyl at the top, COOH at the bottom, hydrogen on the left, hydroxyl on the right, and we will make an asterisk sign because it is chiral carbon. This is the structure of D-lactic acid. Now D-lactic acid rotates the plane towards right hand side, that is clockwise direction. In this compound we will show the direction of rotation. For showing the direction of rotation, that is right hand side, we make an arrow from hydrogen to hydroxyl, and the arrow should be made from the side where the less molecular mass group is present. That is, हाइड्रोजन से हाइड्रोक्सिल एरो हम ऐसे भी बना सकते हैं और ऐसे भी बना सकते हैं, लेकिन हम कौन सा एरो बनाएंगे? जिधर लोअर मोलिकुलर मास का ग्रुप होगा. CH3 will have the mass 12 plus 3 15, and of course COOH will have a higher molecular mass. So hydrogen to hydroxyl arrow will be made towards methyl side. Why? Because methyl is a lighter group, has a lower molecular mass, and you can see that it is dextrorotatory because it is rotating the plane towards right hand side or in clockwise direction. This way we decide the direction of rotation. For making L-lactic acid, you will keep everything same, but you will interchange the position of hydrogen and hydroxyl. So methyl at the top, COOH at the bottom. Now hydroxyl on the left hand side and hydrogen on the right hand side. Right? Now hydrogen to hydroxyl you have to make an arrow. This is lower molecular mass group, this is higher molecular mass group. So you will draw an arrow towards methyl, and you can see that it is anti-clockwise direction. So it will rotate the plane towards left hand side. This is how we show the rotation. And when you are given the question to draw the D or L-lactic acid, it is must to show the direction, otherwise your marks are deducted. So this way, this is dextrorotatory and this is levorotatory. These are the two isomers, optical isomers, in which lactic acid is found in nature. And if we mix 50% D with 50% L, that is आधा ये 5 gram ये 5 gram ये 1 gram ये 1 gram ये, that is in equal amounts, then the mixture is said to be racemic mixture. Racemic mixture of tartaric acid will be optically inactive because it will not rotate the plane towards any side. So racemic mixture is optically inactive, and the reason of optical inactivity is external compensation. External compensation means the rotation caused by 50% D is compensated by 50% L. The amount by which it will rotate the plane towards right hand side, by the same amount it will rotate it back to the left hand side. So the net optical rotation here will be 0. Why? Because external compensation is found here. the rotation caused by 50% D is being compensated by the rotation caused by 50% L. So this way we have D lactic acid and L lactic acid. These are the optical isomers, and the third form can be said to be racemic mixture, but it is not optically active. It is optically inactive. And dextro is optically active and levo is also optically active. Optically active are those which rotate the plane towards any side. So this way dextro and levo are optically active, but this form is optically inactive. This is how we show optical isomerism in lactic acid. When you are asked to show the optical isomers, you will draw dextro and levo, and you can also give an account of racemic mixture. Exactly in the same way, we will see the optical isomerism in the next compound, which is tartaric acid. Tartaric acid, these two compounds are here in our course, lactic acid, which we just saw, and this is the lactic acid isomerism, and this is tartaric acid, which we are going to do. Tartaric acid has the IUPAC name 2,3-dihydroxy butane 1,4-dioic acid. So name is long, but it is not at all difficult to draw the structure. Butane, but means a 4-carbon chain. Ane means all the bonds are single. At 1 and 4 we have oic acid. So 1 को COOH में change कर दें और 4 को COOH में change कर दें, right? And at second and third we have hydroxy. So we will attach one hydrogen here and one hydrogen here. And you can see that this is the structure of tartaric acid. You can be given the question with the name tartaric acid or with this IUPAC name. So you should be able to draw the linear structure, and you can see that this carbon is chiral and this carbon is also chiral. How? This carbon is connected to H, OH, COOH and this whole group. H, OH, COOH and this whole group. This carbon is also chiral because this is connected to H, OH, COOH and this whole group. That is, both the carbon here are asymmetric, which are at position number 2 and 3, that is second and the third carbon are asymmetric. So when it is asymmetric or chiral, then it should show the optical isomerism, but at the same time there are two chiral carbons, so we have to check the second condition also, that plane of symmetry should be absent. So tartaric acid exists in two forms which are optically active and two forms which are optically inactive. So the first form is D-tartaric acid, that is dextrorotatory tartaric acid. Now in order to make dextrorotatory, we will follow this structure where COOH will be drawn at the top, then carbon and at last COOH. It is butane 1,4-dioic acid and 2,3 पे we have hydroxy. So एक हाइड्रोक्सी आप यहाँ लगाएंगे राइट हैंड साइड पे और एक हाइड्रोक्सी आप लगाएंगे लेफ्ट हैंड साइड पे. सो यहाँ पे एक हाइड्रोजन और एक हाइड्रोजन यहाँ. दिस इज द स्ट्रक्चर ऑफ डी टार्टरिक एसिड. नाउ दिस कार्बन is chiral, this carbon is chiral. For this, the direction of rotation is from H to OH. Now एक ग्रुप है COOH और एक ग्रुप है ये इतना बड़ा सा ग्रुप. सो ऑब्वियसली COOH का मास कम होगा, तो इस कार्बन के लिए हम रोटेशन बनाएंगे इस तरह से, डायरेक्शन फ्रॉम H to OH towards the group which is smaller molecular mass. and for this carbon hydrogen to hydroxyl, अब ये वाला मास छोटा है, ये वाला पूरा ग्रुप बड़ा है, तो हाइड्रोजन से हाइड्रोक्सिल आप ऐसे एरो बनाएंगे. That is, this is rotating the plane towards right hand side, therefore it is dextrorotatory. For both the carbon you have to show the rotation. And how is rotation shown? Hydrogen to hydroxyl arrow is to be made, and you will make the arrow in such a way that it is going from the side which is lower in molecular mass. H2OH, one group is COOH attached here and one group is this whole big group. So obviously this will have a greater molecular mass and COOH will have a lower molecular mass. So I drew an arrow from H2OH taking carboxylic into consideration. In the same way, hydrogen to hydroxyl, this is COOH and this is whole big group. So we will draw an arrow from hydrogen to hydroxyl from this side. And both are showing that rotation is towards right hand side or in clockwise direction. So this is how we make dextrorotatory tartaric acid. For making levorotatory tartaric acid, what you have to do is you simply have to interchange the position of hydroxyl इधर, हाइड्रोजन इधर, और इसमें भी इंटरचेंज कर दें. तो COOH ऊपर ही रहेगा और यहाँ पे COOH नीचे. अब यहाँ पे OH was on the right hand side, so now OH is on the left hand side. H was on the left hand side, H on the right hand side. And similarly interchange the position, hydrogen on the left hand side, hydroxyl on the right hand side. So this carbon is asymmetric, this carbon is asymmetric or chiral. Now you will make an arrow for direction of rotation, hydrogen to hydroxyl. एक ये COOH ग्रुप है और एक ये इतना बड़ा सा ग्रुप है, तो ये छोटा मॉलिक्यूलर मास है, तो आप ऐसे एरो बनाएंगे. Exactly in the same way, hydrogen to hydroxyl, this is a smaller molecular mass group, this is bigger molecular mass group. So hydrogen to hydroxyl, you will make an arrow like this, and you can see that it is anti-clockwise direction or left hand side rotation. So this is L-tartaric acid. The third can be mesotartaric acid. Now mesotartaric acid is optically inactive. See, what you have to do, hydrogen and hydroxyl were on left and right hand side and hydroxyl was across. To make meso, you will bring hydroxyl on the same side, hydrogen on the same side like this. COOH, C, C, COOH, right? अब दोनों हाइड्रोक्सिल एक साइड ले आइए और दोनों हाइड्रोजन एक साइड. This is meso. Now we will see that this is chiral carbon. Now let us make the direction of rotation for this mesotartaric acid. हाइड्रोजन टू हाइड्रोक्सिल COOH की तरफ से और हाइड्रोजन टू हाइड्रोक्सिल COOH की तरफ से. Now you can see this is the plane of symmetry present here. Why plane of symmetry is present? Because if you divide it through this plane, you are getting identical halves. There was no plane of symmetry here, no plane of symmetry here. Why? Because this was not as this. Hydrogen was facing hydroxyl, hydroxyl was facing hydrogen, and same is the case in LIVO. So dextro and LIVO were optically active. Both were optically active because plane of symmetry was absent here, but meso is optically inactive because plane of symmetry is present. It is dividing the compound into two identical halves. So I told you that if there are two asymmetric or chiral carbon, then you have to look for the second condition, plane of symmetry should be absent. यहाँ पे absent था, तो they showed optical isomerism. But here plane of symmetry is present, so it will not show optical isomerism, it will be optically inactive. You can see this carbon is causing the rotation towards left hand side, that is anti-clockwise direction, and this carbon is causing the rotation towards right hand side, that is clockwise direction. That is, this part of the molecule is dextrorotatory and this part of the molecule is levorotatory. एक ही molecule में दो different roles, आधा molecule levorotatory, आधा molecule dextrorotatory. That is, the rotation caused by this half will be compensated by this half. जितना ये डेक्स्ट्रो सपोज ये रोटेट कर रहा है 30 डिग्री राइट हैंड साइड को, तो ये वाला पोर्शन क्या करेगा, ये वापस इसको वहीं पे ला देगा. दैट इज़ इन विद इन द सेम मॉलिक्यूल, हाफ मॉलिक्यूल इज़ लीवो, हाफ मॉलिक्यूल इज़ डेक्स्ट्रो. देन दिस will lead to net optical rotation 0, and the reason is said to be internal compensation. Internal compensation means when within the same molecule, half molecule is dextro, half is levo, एक ही molecule के अंदर दो तरह के roles play हो रहे हैं, then you call it internal compensation. So mesotartric acid is optically inactive, that is the net optical rotation is 0, and the reason is internal compensation. And the fourth form may be racemic mixture, and racemic mixture we know is 50% D-tartric acid and 50% L-tartric acid. इसका mixture is called racemic mixture. Here it is also optically inactive, that is the net rotation will be 0, but the reason of optical inactivity is external compensation, because the rotation caused by 50% D is compensated by 50% L. I told you this is external compensation. और जब एक ही मॉलिक्यूल में दो तरह के पार्ट्स हैं, आधा मॉलिक्यूल डेक्स्ट्रो रोटेटरी है, आधा लीवो, then you call it internal compensation. So mesotartric acid will not rotate the plane because plane of symmetry is present here, and the reason is internal compensation. And racemic mixture will also be optically inactive. Here also the net optical rotation will be 0, but the reason is external compensation, because the rotation caused by 50% D is compensated by 50% L. So tartric acid exists in 4 forms. I told you that 2 are optically active and 2 are optically inactive. So the optically active forms are dextro and levo, and optically inactive are meso and racemic. So when you are given to draw the optical isomers, draw dextro and levo and also draw meso and racemic. Give an account of racemic, you don't have to draw anything here, but in meso you have to draw the structure. So this is how optical isomerism exists in tartric acid, and this is all about this topic. So we had to do only 2 compounds for optical isomerism, tartric acid and lactic acid, and we have done this. So this is all for this video. Thank you.